broadcast is now starting. All attendees are in listen-only mode.
Hello everyone and welcome to today's AEE member webinar. We are on Tuesday, November 5th, and we have Rod Yeo with us this afternoon. And I will introduce both the webinar and our speaker to you in just a moment. As always, I just want to go over a few housekeeping things before we get underway. First of all, I am Sharon Hewson. I work here at AEE and I am Executive Assistant to Mr. Bill Kent, the Executive Director here at AEE. And these are member webinars of one of the many things I do here. Today, as you are all listening in, please understand if you have questions during the course of the webinar, we are going to hold questions to the end of the presentation. So all your questions will be addressed at the end. Please post your questions in the questions panel on your control panel. You also have a section for chat. If you have questions directly for me or concerns regarding anything technical, post those in that chat section so that we can keep the questions for me and the questions for the presenter separate. Would appreciate that. And as always, we will follow up with an email in the next 24 to 48 hours that will contain a link to today's recording and to your certificate of attendance. So please be on the lookout for that. And so without further ado, I am going to go ahead and introduce Mr. Rod Yeo. Mr. Rod Yeo is Principal with Mechanical Engineering at Dialogue, and will be presenting Deep Building Retrofits for Energy and Carbon today. Mr. Yeo is widely acknowledged as a leader in integrated practice development and project management. He brings over 27 years of experience in a broad range of project types to Dialogue. He has had much success with multidisciplinary design and delivery build on leadership and growth of Dialogue's integrated practice. Excuse me. The success in his approach is exemplified by a portfolio of sustainable high-performance buildings, including the award-winning City of Vancouver National Avenue Works Yard, which was the first building to be LEED certified by the Canada Green Building Council. Rod graduated from the University of British Columbia with a Bachelor of Applied Science in Mechanical Engineering. He is a registered engineer in the provinces of British Columbia, Alberta, Saskatchewan, Manitoba and Ontario, and the Yukon, and in the states of Washington, Oregon, California, Idaho, Utah, Montana, and Colorado. Mr. Yeo is a sought-after thought leader and speaker, having given presentations at multiple different events, including the Cascadia Green Building Council, BOMA, the Buildings Show, the Design Build Conference, and at Green Build. Mr. Yeo has spoken on a variety of topics, including energy efficiency, commissioning, LEED EBOM versus BOMA Best, energy efficient high-rise buildings, and passive house and net zero buildings. So thank you, Mr. Yeo, for being with us this afternoon. I am going to go ahead and pass control over to you.
Thank you, Sharon. Let's see if this works here. Well, thanks everyone for attending. First thing, listening to Sharon introduce me, I've realized I need to shorten my bio. So thanks everyone. Are you seeing my screen?
Yes, I'm looking at your desktop right now.
Okay, let's see here. There we go. Display settings. There we go. All right, thanks everyone. So my presentation today is on deep building retrofits for energy and carbon, and specifically it's going to be 2 case studies of projects that we've worked on here at Dialogue. So just a quick intro to Dialogue. Dialogue is an integrated firm based in Canada. What we try to do is make sure our projects meaningfully improve the well-being of the communities and the environment in which they are located. This is supported by our mission to do great work, create success for our employees, partners, and clients. Enjoy the journey. We like to have fun while we're doing projects and to make a difference in our communities. As I said, we are an integrated firm, so we have urban designers, planners, architects, interior designers, structural, mechanical, and electrical engineers, and landscape architects. I'm based in the Vancouver studio. For those of you who are good at geography, you can look at the map. We have studios in Vancouver, Edmonton, Calgary, and Toronto in Canada, and a studio in San Francisco that we recently opened. And Dialogue is actually one of the few Canadian firms that have signed on to the AIA 2030 commitment. So that means we are designing all our buildings to try to achieve carbon reductions with a goal of net zero carbon by 2030. And we take this very seriously and are going through all our projects as we go through that. So quick, what is zero carbon? So this is a sort of a high level definition. A zero carbon building is defined as one that is highly energy efficient and produces on-site or procures carbon-free renewable energy in the amount sufficient to offset the annual carbon emissions associated with operations. And for the purposes of this presentation, we're talking about operational carbon. We are starting to look as a firm regarding embodied carbon as well, but these projects specifically deal with operational carbon. So we have a zero carbon balance, this zero carbon transition plan for large institutions, on-site renewable energy, and then a couple of acronyms that you may or may not be familiar with. One of the keys for zero carbon, especially in a cold climate, is a thermal energy demand intensity, or a TEDI target. Basically, that's the measurement of the amount of heating load that the building requires. So it's heating and ventilation load is the thermal energy demand. And then there, obviously we report EUI, peak demand, and then as I mentioned, we're starting to look at embodied carbon. So the first case study I'm going to talk about is the Bikini complex located at the University of Calgary in Alberta. So this project is obviously for the University of Calgary. Dialogue is providing architecture and engineering services, and one of our sub-consultants that's working with us is TransSolar Klima Engineering, based in Germany. They specialize in kind of energy, sustainability, and climate engineering. And the Calgary, Dialogue, and TransSolar have contributed to the slides you'll be seeing today. So just for some context, the site is on the west side of the city of Calgary, the University of Calgary. The actual project site, as you can see by that red dot, is kind of right in the middle of the campus. We see it as the heart, one of the hearts, the heart of the campus, being the main library that's on campus as well. And the University of Calgary has a very aggressive policy regarding sustainability and climate and carbon. So building on the success of their first institutional sustainability plan, in 2016, the university released the Institutional Sustainability Strategy and Supporting Framework. And then back in 2008, the University of Calgary became a signatory to the University and College President's Climate Change Statement of Action for Canada, which led to the publication of their first climate action plan in early 2010. And having realized much progress on the 2010 climate action plan, and recognizing the substantial changes to the environmental technology and energy context, they spent the past year renewing their climate action plan and have recently released their 2019 climate action plan with renewed targets and strategies. So the 2019 CAP, or as they call it, their climate action plan, outlines actions to realize emissions reductions in 4 key focus areas. 1 is new building innovation. 2 is existing building energy retrofits. 3, green power. And then 4, decarbonization of their district energy system. Their zero carbon buildings are an essential part of their new building innovation, but also connect to other aspects of their plan. So the project I'm talking about is it's a existing building retrofit, but it's a major retrofit, as you'll see. So it's kind of a cross between a new building and a major retrofit. So the University of Calgary, 99% of their GHG emissions are actually from their built environment, that is buildings. If you remember the campus map I showed, it's actually a fairly compact campus, so there's not a lot of transportation within the campus, so 99% of the GHGs are from their buildings. To date, they've seen a 30% reduction in absolute terms, despite substantial growth on the campus, 40% on an intensity basis. That's tons per gross square meter is there. So they've seen a 40% reduction on that basis. These reductions have stemmed from energy efficient new buildings, investment in their district energy system, and their efforts to retrofit existing buildings. Going forward, their new building innovation remains an important measure in the university's aspiration to achieve 50% reduction in carbon by 2030. So the Bikini building. So the picture on the right shows the existing or the prior condition of the Bikini building. It was kind of a standard 60s vintage library tower and block. It was very exclusionary, obviously quite opaque, no real visual windows, not much daylight. Very insular, kind of oppressive. Architecturally is kind of brutalist, modern. So some of the goals of the project were to create some urban vibrancy. As I mentioned, the project is at the heart of the campus. Create some connection and linkage to the rest of the campus. Create some culture and identity within the space. Obviously, sustainability and wellness is high on their priority list. Want it to be innovative and aspirational as well, inclusive and open. And as I said, integrate the new facility into the community. So here's a rendering of the final design of the tower. The architectural design idea was to unify the urban fabric, create a new campus heart, soften and reinterpret the dated modern geometry, quite a big change from the brutalist concrete structure it used to be, increase the transparency, and create a community beacon on campus. So you can see from the change from what it was, a modernist, brutalist concrete building, this is now almost 100% glass. And you'll see how we're able to achieve almost 100% glass and reduce carbon in a cold climate like Calgary. So some of the primary drivers for the project scope: renovate the Bikini Tower and expand the floors, replace the block and the link, preserve and enhance the urban linkages and campus integration, as I've said before. And then the program focus on the students and the pedagogy of the campus, focus on sustainability and examination of the potential for net zero carbon. These are the goals that the university came to us as dialogue with. And then revitalization of the Swan Mall, which is where the area in which the project is located. So the original structures, built as a library tower in 1968. The tower was originally only 6 floors, but expanded vertically in 1971 with the addition of 6 additional floors. They were projected to go to 22 stories at some point. The concrete superstructure and precast cladding and curtain wall envelope, that was kind of the makeup of the building structure. And as I mentioned before, and from the pictures, you can see it had a very low window to wall ratio. And the envelope and the mechanical and electrical systems at the time we started the project were in pretty bad repair and beyond the serviceable life. So this made the building a good candidate for a full retrofit. The envelope being at the end of the life was a key driver in how we were able to achieve the net zero carbon targets that we're trying to get to. So for every project, and this is where TransSolar was a key. We actually do this for most of our projects. Sometimes we use TransSolar and other consultants to help us out. But for every project, we try to look at the site and the climatic conditions of the site. We strongly believe that our projects need to work with the location, the geography, and the climate in that space. So it starts with a solar analysis. What you're seeing on the screen is a sun path analysis of the site. So, and then we like to start looking at passive strategies first, try to make sure we reduce loads as much as possible. With that, we look at the massing of the building, how we can get shading, solar orientation. Building orientation, as I said, solar access and solar gains and control. Building orientation in regards to wind, if we look at natural ventilation and other ways to use wind as a way to move air. Open space access, some program distribution, how you distribute program within a building can affect energy use and carbon use as well. And then obviously we're looking at daylighting and natural ventilation as options as well when you're looking at passive strategies. So this is some of the work that TransSolar did with us. Basically, it's an analysis of the climate analysis, of the potential for solar radiation on site. So the charts, there's quite a bit going on in this graph, but the top left is the annual total solar radiation available on a kilowatt hours per square meter per year basis for the horizontal solar panels. The drawing on the bottom left kind of shows the solar radiation capacity and sort of on the areas of the building. And then being based in Germany, TransSolar kind of compared the Calgary climate to Berlin, which is what they're used to. And they actually found that Calgary has a high annual solar insolation on horizontal surfaces and south-facing facade. And that Calgary actually has better solar access than Berlin and is actually the first or second in Canada as far as annual solar access. And here's some additional analysis on various facades for vertical facades. So these are solar panels on the vertical at 90 degrees. As you can see on the south side, southeast and southwest facades, there's actually quite a bit of potential, high solar potential on the southeast and southwest facades. And kind of obvious, but we needed to run the numbers to show the client that there's low solar potential on the northwest facade. And another analysis we looked at was kind of the temperature swings, annual temperature swings in Calgary. Those of you who have been there know that it gets quite cold in wintertime. We're approaching minus 30 quite frequently in the winter as a design low. But in summer, it gets quite warm as well, over plus 30. So there's a delta T of about 60 degrees Kelvin or Celsius in this case through the year for Calgary, which is quite a wide swing. And the other thing we looked at was the diurnal temperature swing, which is the difference in temperature from daytime to nighttime. So the chart you're looking at shows the outside air temperatures and absolute humidity through a representative period in summer. As you can see, we took a time from July the 20th through July the 27th, a week of sort of peak summer design conditions. And you can see where the delta T is about 15 degrees Kelvin or Celsius, from the overnight low below 15 degrees to a high during the day of over 30 degrees. So we looked at this and saw that this big temperature swing during the summer made the building a good candidate for night flushing or night cooling. So all that analysis of climate and location and all the things sort of led us to what we could use to reduce carbon in the building. So as you saw the summary, there's a high solar potential also during the winter on the vertical facades, and especially on the south side. As I said, there's a substantial diurnal temperature swing from day to night through the summertime. And there's relatively low humidity levels during summer, so humidity control wasn't a big deal, as big an issue in Calgary, unlike some of our other climates towards the east, like Toronto or Ottawa or Montreal. So all those things led to our design for passive solar utilization of the sun, especially on exposed building facades. It affected our facade design. Active solar applications on roofs and facades. Natural ventilation, use the wind where we can. Passive cooling by night flushing. There's a high benefit from the use of thermal mass. So basically, we took the building, stripped the envelope and mechanical and electrical systems, and left the concrete structure. So there's still quite a lot of thermal mass in the building. And as I mentioned, there's no humidity problem in the summer, so we could use evaporative adiabatic cooling. So one of the next big design decisions we're looking at was a double facade versus a single facade. And I mentioned previously that we're able to achieve very low carbon and energy use with an all glass, pretty much all glass building. And really the only way we were able to do that is with a double facade. So we analyzed the difference between a double and a single facade using, on the double facade, we looked at an exterior double or triple glazed units, interior single glazing with a large gap in between, which I'll go into more detail later. Operable solar shading in the double facade cavity. We did some analysis on that as well. Natural ventilation of the double facade cavity by the operable openings. And then basically that double facade space serves as a climatic buffer space. And versus a single facade, we kind of looked at double or triple glazed single facade. Interior operable solar shading to control solar load, and then operable windows. Kind of we compared the two. And these are some of the results of the comparison. Again, quite a busy slide, but the key graphics to note here are top left and bottom left are sort of the double and single facade options. And the key to note is the vertical axis is the inside temperature of the spaces, and the horizontal axis is the outside air temperature. And the green dots are basically kind of plotted conditions through the course of a year. As you can see in the blue line is the sort of the upper limit of comfort conditions we're trying to maintain within the space. So as you can see with the double facade providing that buffer space and climatic buffer, we were actually able to maintain comfortable conditions inside most of the year, whereas on the lower left you can see there's quite a few points that are too hot outside in a single facade. This is just looking at the building without actual mechanical cooling or heating. So we like to do that when we look at projects. We do run a comfort conditions without any mechanical heating or cooling just to see what the building would behave on its own. So basically that's kind of the design ethos for the project, was a well-tempered facade, basically putting a warm jacket around the building, around the existing building structure. So you can see that some pictures of the existing building. We're taking off the precast cladding and starting to put the facade on the far right picture there. As I mentioned, we also realized there's quite a bit of solar potential on the vertical facades. So there's horizontal PVs on the podium roof to provide partial EUI offset and part of our net carbon zero carbon plan. And then vertical PVs or photovoltaics placed in the exact locations to leverage high solar intensity on the southeast and southwest facades. And then part of our facade design was also these apertures. As I mentioned previously, part of the goal of the building is to kind of connect to the campus and create visual connections. So from within the library, these apertures provide occupants to be able to see key parts and points of the campus, and that's what these apertures are for. As I mentioned, the double facade we put on, just some quick details. The building kind of slopes in at the top, so the detail on the left shows the stepping in of the building and the facade near the top of the building. The detail on the right shows the double facade with the single glazing interior and the triple glazing exterior, which I'll show in more detail in the next slide here. So as you can see, this is kind of a blow-up detail of the double facade. On the right, we have the single glazed interior single facade. Then we have a space of approximately 1,200 millimeters, 4 feet roughly. And then the triple glazed exterior facade with openable windows, which allows ventilation of that facade space. And then there's a built-in integration of solar shading in that space as well, in the interstitial space between the two facades. So that's kind of the passive methods of trying to reduce load. Now we're looking at active strategies to influence the performance of the engineered building system. So we're looking at radiant systems with radiant panels seen in these pictures on the left and on this sort of in the middle, as well as PVs and low intensity lighting and LED lighting in there. So a quick schematic of kind of the mechanical systems and the way it works with the building envelope. We've got, as I said, exterior triple glazing, blinds and shading within the space, interior laminated single glazing, and then interior low E coating on that coat. And then the glazing performance, all these values are in metric, but visible light transmittance is quite high. Center of glass U value of 0.55 watts per meter squared per Kelvin. Just for reference, that's roughly about 0.01 BTUs per square foot per degree Fahrenheit, which is a very, very low U value. Note that's for the entire assembly of the triple glazed large airspace and the single glazed. Solar heat gain coefficients of 0.49. And then with the activated blinds, very low solar heat gain coefficient of 0.06. And from a system point of view, you can see we've got an underfloor air distribution system for ventilation air, radiant panels in the perimeter for heating, and radiant panels in the interior space for cooling. We've tried to leave as much of the concrete structure exposed as possible for concrete for storage and thermal mass. And then, as I said, the operable windows create venting of the facade so that we can try to control the temperature of that interstitial space. And just a quick rendering of trying to glare control and user control and shading as well to try to look at the daylight. So here's a rendering of the indoors with the daylighting possible and some glare control with the sort of diagonal elements that are there to try to control some glare as well. So the double facade operations strategy is, like I said, create a warm jacket around the building, enable some natural ventilation through the space when conditions permit. As I said, we're trying to maintain the air temperature in the double facade cavity between 10 and 20 degrees Celsius, limit pressure differences, and then control the air velocity in the facade cavity. So, as I said, there's some keys to zero carbon performance. The thermal energy demand intensity is a key number. As I said previously, it's a space heating demand, including ventilation and infiltration. So there was a target, we had a targeted less than 36 kilowatt hours per square meter per year. Our design target was about 25 kilowatt hours per square meter per year. And then on-site renewable energy generation to try to make up that zero carbon. We're targeting greater than 5% of the energy was the original target. The final design targeting over 35% of energy created. So a rendering of the final project building kind of fully together. We have a proposed solar PV estimated generation capacity of about 227 megawatt hours on the roof, and about 432 megawatt hours on the block roof, and then a facade about 120 megawatt hours. So here's a kind of the carbon balance for the project, 800 tons of carbon created roughly annually. And then we're trying to make up 312 tons with on-site energy. And then the rest, 488 tons, University of Calgary is making an off-site renewable energy investment. Calgary, Southern Alberta has a lot of wind power, and that's where the university is going to invest in renewable energies to make up the rest of the carbon. So that's kind of the McKimmie complex building, and I'll move to the next case study. So the Canadian federal government has a program to retrofit all its buildings eventually to be carbon neutral. And these projects all start with studies where they study and model the baseline and 4 bundles of energy conservation measures on a life cycle basis. So the baseline obviously is the carbon emissions for the existing building as it stands. Option 1 is to look at minimal departmental standards, which requires about 24% below the National Energy Code for buildings, which is roughly based on ASHRAE 98.1. Option 2, bundles of measures that are cost neutral with the baseline from a life cycle cost perspective over 25 years. That's kind of seen as the minimum efficiency upgrades bundle. Option 3 is a bundle of measures that achieves maximum energy and carbon reductions regardless of life cycle costs. So that's kind of what's the best we could possibly do if our only goal was to reduce energy and carbon as much as possible. And then somewhere between option 2 and 3, usually we come up with the option 4, a bundle of measures that provides maximum carbon reductions while maintaining best value from a life cycle cost perspective. As I said, it's usually a combination of measures from options 2 and 3. So that's the studies that are done on the buildings before and then once the option 4 is chosen, they move to implementation of the option 4. And this is a project that Dialogue has been hired to do the implementation for. It's the Arthur Meehan building in Toronto. Those familiar with Toronto, Lake Ontario to the south, Toronto kind of downtown area, and this is a little bit north of the downtown core of Toronto. So here are some targets, 66 kilowatt hours per meter squared target of EUI, a LEED NC Gold candidate, WELL NC Silver candidate, target of 81% reduction in operating GHGs, and then the Canada Green Building Council has a zero carbon building design and performance pilot project, and this project's one of the pilot buildings in that program. So by the numbers, the gross floor area is roughly 35,700 square meters, about 70,000 square feet. It's quite a large building. A number of floors, about 10 floors with a penthouse and an underground parkade. Buildings actually made up of 2 buildings constructed at 2 separate times, 25 St. Clair and 55 St. Clair. Construction is ongoing currently, and anticipated occupancy for the final product is in 2022. And as I said, our target GHG reduction is over 80%. So quick sort of snapshot of how we're achieving these targets. The main contributing factors are a good building envelope, 330 kilowatt capacity rooftop PVs. As I said, high performance enclosure, we're looking at about R28 walls, R30 roof, and triple pane windows targeting about U of 0.15. These are imperial numbers. In Canada, we switch back and forth between metric and imperial depending on the time of day. But we're also doing a geothermal field installed below the building, including about 53 boreholes, about 600 feet deep each. We have a high efficiency HVAC system with heat recovery chiller and dedicated outside air system. And then activity-based workplace and circadian lighting and ergonomic workstations from the wellness point of view for the occupants. So from the envelope design perspective, we kind of looked at with the 2 separate buildings, looking at the sun daylight access, and then we're trying to create a stepped connection across the 2 buildings. Breaks up, it speaks to the transitioning towards a visibly sustainable government building. Materiality of the glazing to provide visibility as 2 separate buildings of 25 St. Clair and 55 St. Clair. That's kind of, so there's a bit of a visual step through the building, as you can see in the picture here. And some more pictures of just the facade design and the steps. So one of the other things we looked at, the building is quite a big floor plate, and the floor-to-floor heights are, they're not generous. They're not small, but they're not generous either. So as we said, we looked at an underfloor air distribution system to start with, but with the structure, the return plenum in the ceiling, and the underfloor plenum, that resulted in ceiling heights slightly under 8 feet, which for a large floor plate office area is quite low. So we looked at just a standard overhead system. Again, with the large ducts and everything we'd have to put under the existing structure, it's resulted in slightly higher, still an 8-foot ceiling. So in order to try to maximize ceiling height, we started looking at kind of distributed mechanical modules throughout the building. That way we'd have to run lots of ductwork throughout the entire building. Sprinkler and lighting could be sort of recessed into the pockets above the beams in the structure. And then we were able to create 10-foot ceilings in most of the space. And what these mechanical modules kind of consist of is kind of a standalone neighborhood of HVAC. It's basically a vertical source heat pump tied to distribution ductwork that kind of blows air across the modules, return air gets sucked in, and then, like I said, it creates higher ceiling spaces throughout the space. You can see on the plan on the right, these modules are located throughout the fairly large floor plate. We do give up a bit of floor space with these modules, but it was together with the client, we decided that the floor space loss was worth the increased height in the ceiling. And then from the vertical air distribution point of view, we're feeding from the DOAS, or the dedicated outdoor air system, from a central or a couple of central heat recovery ventilators located on the roof and distributed throughout the building vertically. And then we kind of geo exchange system, as I said, we have a sort of a boreholes and ground loop system installed. We started looking at options for how this system could go in. Option one was to work in the mechanical pit, where there's a high overhead clearance with mechanical equipment will be located. Option two was to drill down vertically from the existing parking levels. And option three was to start at grade level outside the building and drill vertically down or diagonally under the building. Option three ultimately was not pursued, as the cost and coordination required drilling on a busy street was not feasible. So basically, we decided to go with options 1 and 2, both from the mechanical pit and from the parkade, drilling straight down. We have drillers now that have very compact drill rigs that specialize in drilling boreholes in existing parking garages and sort of tight spaces. So that they were able to drill these holes. Takes a bit longer, but 600 feet deep, as I said. So one of the issues with ground source or geos exchange system is you need a balanced load. And for an office building, even in a cold climate like Toronto, we found that it's a cooling dominated building, so the loads aren't super balanced. So just as an anecdote, I live in Vancouver. I'm in the Vancouver studio, and we've actually had ground source heat pump systems here for quite a long time. Some of the first systems to go in the Vancouver area were at schools, kind of in the early 90s or late 80s. A bunch of ground source heat pumps went in schools. And because schools tend not to have a balanced load, they are occupied through the winter. They're actually not very occupied in summer, so they're actually heating dominated. What they were finding here on those old systems were that we were cooling the ground off too much by sucking too much heat out during the winter and not putting enough heat back in during the summertime. So lessons learned from those old systems, we've learned that we really do need a balanced load so that you pull out as much heat as you put back into the ground. So over the course of a long period of time, 10, 20 years, you don't end up cooling or heating up the ground too much. So in this case, as I said, we've got an unbalanced load. So we need to deal with the cooling some other way other than just the ground loop. So we've developed kind of a hybrid cooling system with the ground loop tied into heat recovery chillers and a fluid cooler, which I'll show in a little more detail here. So here's a blow up of the geo exchange section of the loops through some pumps through a heat pump chiller, and the secondary pumps tied into the chilled water loop. And then, as I said, part of the main chilled water system, there's a cooling tower up on the top as well that provides additional cooling when we don't want to cool the ground off too much or heat the ground up too much. Sorry. And that's kind of it for the presentation. Happy to take some questions now. Trying to look at the questions sheet here. Okay, there's one asking me to adjust my microphone. Hopefully you can hear me. Sorry, I'm having trouble getting the questions to show up. Sharon?
I'm sorry, I was muted. If you click on the questions bar and drag it, you can pull it off to the side and then extend.
There we go. Okay.
You have them?
Yes. Okay, the first one was regarding the microphone. Hopefully you can hear me better now. Hi, question one. Along with primary drivers you mentioned for the project of the university, was Or is there any obligations or incentives set by the government that motivates the development of such projects? That's a good question. So our federal government has provided funding for carbon reductions. As part of that, there's been a lot of funding available to post-secondary institutions, which the University of Calgary did take advantage of. Now, I will say it was some funding, but it was nowhere near enough to pay for the double facade. The double facade, I will point out, is a fairly costly option, and the University of Calgary was willing to go down that road to try to prove what could be done as a kind of a test and pilot project. But to answer the question, yes, there is some funding available for the federal government. Second question, can we get a copy of this presentation later? Yeah, I will send a copy to Sharon, and she will be able to distribute it to people who ask for it. Third question, how do you monitor and control inside temperature change and its effects on energy consumption and hence GHG emissions? I assume that's referring to the Calgary project. Radiant systems, we are controlled fairly similarly, but again, we leave it up to the occupants to have some control over their temperature, but typically we allow a 3 degrees Celsius kind of range of operation so that nobody can really crank up their thermostats or crank down the thermostats. And radiant systems, one of the benefits is they tend to be more comfortable. We're actually members of the Center for the Built Environment at Berkeley, and they've actually done quite a few studies on radiant buildings. And their studies have shown that thermal comfort in radiantly heated and cooled buildings tend to be better than thermal comfort in air source-based systems. So that helps people not play with the thermostats too much. Fourth question down. Please define night flushing. Oh, yeah, sorry. So night flushing is basically trying to move as much air through the building at nighttime as possible using the outside air temperature to pre-cool the building. So basically, we move air through the building at night when it's cool so that we can cool the thermal mass of the concrete down. And then by the time morning comes around, the thermal mass of the concrete is cooled down. The surface temperatures are quite low, and it takes quite a while during the day for those temperatures, the surface temperatures, to heat up again. And so it provides a lot of cooling. In fact, projects we've done it on, we sometimes have to check that we don't overcool the building at night because you know, as you saw from the graph, it was 15 degrees Celsius at nighttime. If you flush it all night, you could get surface temperatures as low as 15, and that's actually too low. When people come into the building in the morning, it actually feels too cold. So we have to actually make sure we don't overflush the building. Please explain the difference between a double and single facade. Yeah, sorry. So basically, the double facade is the way you look at it is we have a traditional building has a single facade. Now that single facade could be glazing with walls, and the glazing could be single, double, or triple pane glass. In a double facade, you're basically building two building envelopes. So you have got the sort of what we consider the traditional building envelope. I'll go back to the slide so you can see it better. Hold on. Sorry, this is taking longer than I thought. Hold on. There we go. So, can you see my cursor? Sharon, do you know if my cursor shows up?
Yes, it does.
Okay, so on this is what we consider the traditional building envelope, the single facade. So if this were a single facade building, this basically right here would be the traditional buildings envelope where the glazing and the wall would go. In this particular case, this is only a single glazed sort of glass panel. This out here is the second envelope that we've built exterior to the the first facade, which is the triple glazed envelope system. And this creates a large buffer space in between the two facades. And I did mention this I'm not sure this will be, there's actually a question further down that says 4 feet seems like a lot of space. The reason this space is 4 feet is for service and maintenance. So somebody needs to get in between the two facades to be able to service any operable windows, clean the glass. So that's why it's 4 feet. 4 feet is a lot. It could be maybe 3, but we felt 4 feet was better, easier to get people in and into the space to service it for. So that was the next question, was the 4-foot spacing. Next question, what equivalency ratio was used to quantify tons of GHGs diverted from atmosphere? I'm speculating. I think equivalency ratio you're referring to as carbon intensity of various sources of energy. And I don't have the numbers in front of me, but Alberta actually has quite a high carbon intensity for electricity. There's still quite a few gas-fired and I think even some coal-fired generating stations in Alberta still. So we use the local GHG factors when we look at carbon from the energy use point of view. So as an example, as I said, I live in Vancouver, which is in British Columbia. British Columbia has a lot of hydro power. So our GHGs our GHG intensity for electricity is quite low compared to Alberta. But from a long-term point of view, we are switching to electricity in Alberta as well, because it's much easier to provide renewables from the electricity side. So if we switch the heating to electricity, we can create PVs, add PVs, wind turbines, and Alberta is starting to green their grid as well, so reduce the carbon in their grid as well. So even though currently the carbon intensity of electricity in Alberta is fairly high, we are switching for future as far as decarbonization of the grid. Another question down below, can you expand on offsetting with reinvestments? Is this just carbon offsetting or is there actual monetary investment? So for both projects, carbon is the main goal, reduction. You know, one is the University of Calgary with some funding from the federal government. The second is the federal government itself. So as I said, the Liberal government that's been in power for a while in Canada has very aggressive carbon reduction targets, so there is funding available. But that said, for the federal projects, which was my second case study, as I said at the beginning, they do evaluate options that are reasonable from a life cycle cost perspective. As I mentioned, so option 3 is what's the best we could possibly do, cost money no object kind of way, and then the final decision is made using a life cycle basis to make sure that the decisions we're making, because it is government money, is makes sense and is saleable to the constituents. All right, and next question down. It looks like about 17 HVAC units per floor. Can you comment on how that affects capital costs and maintenance? So I assume that you're talking about the Arthemian building with the sort of modular HVAC units per floor. Yeah, there are about, I can't remember the exact number, but there's quite a few more smaller units per floor, but that wouldn't be that different than, say, a building with a fan coil system or a building with water source heat pumps or distributed heat pumps. As I said, those sort of modular units are smaller, kind of lower maintenance unitary units. And there's always a trade-off between maintenance of one large unit versus a number of small units. But as I said, the large floor plates and the ceiling heights was important enough that the government was willing to accept a slightly higher operational and maintenance costs as far as those smaller units. Next question down. Can you re-describe that hybrid cooling system again, please? Yeah, it's pretty simple. I'll go back to the, you know what, I think this is probably easier if I do this. So I won't get into too much detail, but the hybrid system basically has, we've tied part of the cooling system to the ground loop. through a heat pump chiller, and that'll be our primary source of cooling. But we've also got heat recovery chillers and a fluid cooler or cooling tower tied to those chillers. So this is more of a traditional cooling system. So we only use the geothermal loop as the primary source. I can't remember exactly when we switch over, but when we get higher loads, then we start using the traditional system so that we don't, as I said, overcool the ground. Overcooled. We're overheat. Sorry, we're dumping heat back into the ground in the ground source system. So hopefully that answers that question. Next question down. How did you do the feasibility analysis of geothermal system on an existing building? I'm going to speculate, and when you mean feasibility analysis, are you speculating that you mean the feasibility of actually installing ground loops in the existing building versus just the we did do energy models. We did look at kind of the efficiency of the ground loop versus an air source heat pump, say. The feasibility of actually drilling the holes, we looked at with, as I said, there's companies that specialize in that, so we got them involved, looked at rough costs for various methods of drilling to see what the feasibility was there. And as I said, the final option of drilling through the parkade and in the mechanical sort of pit rooms turned out to be the most cost-effective way to do those. What modeling software was used? We typically use IES for our energy modeling, Integrated Environmental Solutions. We also use Energy Plus for high-level modeling and various other things. We use the tool that best suits the project, like I said, but sort of our go-to IES is our modeling software that we use in-house. If the question is regarding what Trans-Solar used for the climate analysis, I'm not sure of that question, so I apologize for that. Next question, what kind of CHP systems have you worked with? CHP, I assume you mean combined heat and power. We have used combined heat and power systems in the past. As far as systems go, basically it's a system that generates electricity while providing, and then it's basically an engine that generates electricity, and then we recover heat off that engine to provide heating water for heating as well. Looking at time here, we've got about 8 minutes left. The next question, description of a hybrid cooling system is a bit fast. Can you go over that again? That was, hopefully I went through it again and that answered that question. Next question, is a tour of 55 St. Clair possible? Curious to see it in person. We can check. I'm not sure about that because it is a federal government building. They have pretty high security clearances. I'd have to say offhand, probably not. Next question down, what is the electrical offset for the government building? I'm not sure what is meant by electrical offset, but I will say that, if we're trying to reduce the carbon emissions by 80%, which means quite a large reduction in the energy use because we only have 330 kilowatts of solar panel on the building. So if you mean sort of reduction in electrical use, we're probably looking at 50 to 60% reduction in electrical heating load in heating energy. And you look at the if you look here, the TEDI target is quite low at 17 kilowatt hours per meter squared per year. Just for reference, TEDI of 15 is a passive house. So the passive house requirement is heating demand, which is basically TEDI of 15. So you can see we're trying to get to very low levels of heating load requirement. Next question, could you please share slides of the hybrid cooling systems? As I said, yeah, all these slides will be available through Sharon after the webinar. Next question, what do you think about ceiling radiant panels for space heating? I've been in a new building with this technology that was uncomfortable on top of my head. Yeah, and that is possible. The key is to run the panels at a reasonable temperature. So we try not to run even ceiling radiant panels above, say, 90 degrees Fahrenheit. Even that's a bit warm. We try to keep the temperatures low as possible. They can go up to 140. We have run them at 140, especially in some of our colder climates. But you're right. At those high temperatures, if you're sitting right underneath them, they can feel hot. So you do need to design them carefully. You locate them, especially the ones that are just for perimeter losses right at the windows. You can run those a bit hotter if there's no desks right up against the windows. But if there's desks or people right underneath them, we try to use a lower temperature.
Okay, Rod, we're at 2:54. We've got about 6 minutes. I do have a couple of announcements at the end, so I'm just going to let you maybe select one more question to answer, and then I'll explain how to handle any unanswered questions.
Let's see. I'll see if I can pick one that I think everybody will be interested in. Everybody's interested in cost, so there's one about cost. Do you have a cost for the Bikini building project? I don't have it offhand with me, but I'm pretty sure that information is public. We just have to double check with the client. And I will just leave up my closing slide quickly so that people, if you have any further questions that I didn't get to, or that you have some, sorry, I'm just trying to make this work here, some additional questions, feel free to contact me at the email address listed here. And I'll try, if the client is okay with it, we can share the construction cost for McKimmie as well. I will say that the double facade was a pretty big cost. If the client's okay with it, I will share that cost with anybody who asks. I'll turn that back over to you, Sharon. Do I need to stop sharing? Sharon, I think you're on mute.
Sorry, can you see my screen?
Yes.
Okay, so I just have a few closing comments. I just want to, first of all, obviously thank you, Mr. Yeo, for being with us today, and we truly appreciate your time and expertise in sharing that with our members today. Those of you listening in, I did say at the beginning, but I will reiterate, you will receive a follow-up email in the next 24 to 48 hours that will contain a link to your certificate of attendance and a link to the recording of today's presentation. If you would like a copy of the presentation, Mr. Yeo has kindly offered to provide a PDF copy, which I will have, and you may email me, and I will put that also in the follow-up email. So just before we close today, just a couple of things I wanted to make you aware of. We do have our new AEE Career Hub up and running. We have been asked about this several times so far this year. We've got people, members, and people looking to employ. So we have job seekers and employer options. And if you are a member, you may post resumes for free. Or jobs for free. So you can see right there how you can access that, and we're quite excited about this and would like to see this up and running and active. So please check that out if you are looking for a job or you wish to post a job. Our training schedule for 2020, our live US public training schedule, is now available and is online and open for registration. So please take a look at our offerings, and we'd love to see some of you at our training sessions. In addition, AEE East, which takes place in April in Cincinnati, Ohio, is also open for registration. We currently have early bird member pricing for $95 only, and that price will remain active until the 1st of January. After that time, that price will increase as we get closer to the actual event. So if you are interested in that, please consider going ahead and registering early. And our next AE member webinar will be in December. We have one on Thursday, December 5th. It will be with Bo Griffey from Train, and he will be presenting renewable energy hybrid solutions behind the meter. So I hope that many of you will join us again for that next one. So all it remains for me to say is thank you to anyone and everyone who logged in today. We appreciate your time, particularly yours, Mr. Yeo, and I hope everybody enjoys the rest of their day, and I will be signing us all off now. Thank you.
Thanks, Sharon.
Thank you.
Bye.
Bye.